It's a great pleasure to welcome Jorge Lauret of the Universidad Nacional de Córdoba, who will speak on prescribing Ricci curvature on homogeneous manifolds. And just a reminder, the meeting is being recorded.
Okay, so thank you. Thank you, Caroline, for the presentation. Thank you to the organizers for the invitation to this great seminar. Okay, this is joint work in progress with Cynthia Will, who is here. She's the only one who actually came to the talk. And okay, let's see. So the prescribed Ricci problem. Take M a differentiable manifold. Take this other M, the space of all Riemannian metrics. It's an open cone in this vector space of all two tensors, symmetric two tensors. Okay? And the problem is this: given T, a tensor, the existence and uniqueness of a metric such that T is the Ricci tensor of this metric. It's a classical problem in geometric analysis, okay? And okay, we had to remember all the time that the Ricci tensor, I mean, you're prescribing only the tensor, okay? And the tensor by itself is not the Ricci curvature, okay? It doesn't have eigenvalues, it doesn't have a trace. Only versus the metric is that you get the principal curvatures and everything, okay? So, for instance, this property here is the first non-geometric property, if you want. Is the Ricci tensor, I mean, doesn't know about scaling, okay? And for instance, you can have two solutions to this problem, with one with positive scalar curvature and the other one with negative scalar curvature. Okay. So, okay, the Ricci tensor is not really the Ricci, it's almost, but only versus the metric is the curvature, okay? So, because of this scaling invariance, we also have this, that if for product metrics, you will always have these two parameter space of metrics going to the same tensor. So uniqueness will never hold, okay, in the product. So you will see in many statements irreducibility, okay, as a hypothesis of the metric. Then, on the other hand, we have this diffeomorphism invariance that, and this of course has a geometric aspect, because if you are trying to think in what would be a sufficient condition, for instance, for a T to admit a solution, then that condition should be geometric. I mean, should be invariant by diffeomorphism, okay? In this sense, okay? So you have some, of course, some geometry there. Okay, so this PRP one, you can think about it by studying this function, the function Ricci. And so the problem is asking about the image and the injectivity of this function. So, and then you can try to apply the inverse function theorem or things like that, thinking as a function. And this is a nice question. This is, which are the tensors, if you want, that are so special that they determine the metric, okay? That there is only one metric, always, of course, up to scaling, with that Ricci tensor. Okay, so this is a second version of the problem when you try to, in some sense, compensate the scaling invariance of Ricci with this constant C. Okay, so you ask for a metric and a constant. Okay. And actually we'll be talking about this problem most of the time. The existence now is equivalent to the image, the image of Ricci, but up to scaling, okay, up to scaling. In the sense that there is a solution for T if and only if now T is this, is a positive multiple of some element in the image, okay? But this, in principle, auxiliary constant C creates some problems with the uniqueness. Okay, so it's incredible that this question is wide open. Which are the possible constants you may have here for a given T? Okay, with the existence of a solution. If it is bounded above or below this set, if it is finite, we only know, we will see in a minute, that it's bounded above, but below is open. So let's see some known results, also classical results from the 80s. The dRic proved the local solvability for T non-singular, okay, but locally, okay. This is like metrics on Rn, on an open set in Rn, okay. It's a PDE, right? It's a PDE, okay? As you see, this is a PDE. And then Richard Hamilton, for instance, proved that the round metric is determined by its Ricci tensor, which is G because it's Einstein, right? But so this is a very, very special tensor in this sense. Then, well, at the same time, I think, I don't know, the dRic and Koiso generalize this result for any reducible Einstein metric on a compact M with sectional non-negative. Okay, is also determined by its Ricci tensor. Then we have this non-existence result, which is if T is itself a metric, so T is a positive tensor, and then it has curvature, and its sectional curvature is very small, then there is no solution. Okay, this implies that this set of possible constants is bounded above. Okay, because you start to multiply T. If T is too big, let's say like this: if T is too big, no solution. But bounded below is open. We also have this, in the general case, this variational principle proved by Hamilton, that G bar is a solution for a given T if and only if it's a critical point of this functional. Very simple functional, of course, M compact, so you can integrate here. Okay, so let's talk now about this concept. We are not sure about the name yet, so any suggestion? We call Ricci locally invertible to a metric G bar if, well, this is the definition. If there are open neighborhoods of G bar and the Ricci tensor, okay, such that the following conditions hold. First of all, Ricci of U is a submanifold of codimension 1. Okay, recall that the set of metrics is open here. So we have the same a function between two manifolds of same dimension. And so we are asking for maximal rank, if you want here. Okay, maximal rank, because recall that Ricci is losing one dimension because of the scaling invariant. So this is the maximum you can get. And for any T in V, there exists a unique constant such that there is a solution in U, in the close near to G bar. Moreover, we ask that solution to be unique in U. Okay, so that's the definition. Is just this. I mean, it looks complicated, but it's just that Ricci is as surjective as it can be, as injective as it can be, locally.
Jorge, question. Which
Yes?
topology do you use with metrics?
No, everything the usual. We will, of course, go to the homogeneous case where everything will be finite dimensional. But here is the usual. It's a Fréchet space, is manifold. Okay, the usual one. The infinity. So it must be question. Yes.
Can you explain why are you restricting to positive C?
No, just for not changing the signature of T, but yeah, you can do it with any C, but yes, it's just convenient. Sorry? Okay, so we must be careful because we are talking locally here. So there may exist, and we have examples, there are examples, another constant C prime with another solution G prime just outside of U, okay? That happens. So the following metrics are known to be invertible. Hamilton proved that the round metric on the n spheres, the dRic, the irreducible symmetric spaces of compact type. Actually, any Einstein metric with this is the Lichnerowicz Laplacian, satisfying that the kernel is just these multiples of G. For instance, if it is irreducible and of non-negative sectional, you get this condition. And delay and Herzlich, in the non-compact case, they prove for real and complex hyperbolic spaces, and actually any rank 1, this Ricci local invertibility. Okay, so let's go to the homogeneous case. Take M a homogeneous manifold, choose G and fix G, one of the transitive Lie groups on M. So MG is the set of of all G-invariant metrics. Everything will be G-invariant from now on. So it's known that MG is a submanifold of this finite dimensional vector space, which are these symmetric to tensor but G-invariant. Okay. It's even a symmetric space. And the dimension is between 1 and this. Okay, n is the dimension of M. So it's 1 with when you have an isotropy reducible homogeneous space, and you get this when M is the Lie group G, and you are working on left invariant metrics on G. Okay. So the prescribed Ricci problem for G invariant in the G invariant case is exactly the same, just that everything is the tensor and the metric are G invariant. So this is the problem. This is a remark I like to make because, well, as you see, it's like we are. I mean, T is G invariant, and we are looking for a solution which is also G invariant. But it may happen that the Ricci tensor have more symmetries than the metric. Okay, so it may happen that you don't have a solution, a G invariant solution for a G invariant T, but you may have an H invariant solution for some subgroup H. Okay, we'll come back to this phenomenon many times in the talk. So, well, the existence in this case is of a solution for Chi. We can define this function, which is just multiply the Ricci function by the determinant of the metric with respect to some background metric G naught. Okay, you can fix G naught and define this Ricci tilde, and so I mean is to break the scaling invariance of Ricci. Okay, but then now the solutions are the image of this Ricci tilde, and because the image is just the positive multiples of the image of Ricci. This is a remark that sometimes it's like you may understand perfectly the image of Ricci, and of course these are all the solutions for the PRP2, but this is just a virtual, if you want, definition of this set. Virtual, like this seminar, definition of this set, and sometimes it's very hard to find the I don't know the description. Yes, a good description for this set to answer some questions about if it is open or not in some cases. Okay, so. And well, the injectivity, it's easy to see that the injectivity of this Ricci tilde is equivalent to the uniqueness, okay? Where uniqueness for this problem means this, okay? The pair is unique, always up to scaling of the metric. Okay, so this Ricci tilde seems to be the function to study, to try to apply the inverse function theorem or some other. Well, here we have some questions, natural questions. The red ones are open. Recall then the problem and the function Ricci tilde. Well, in all examples, we know C is unique for Chi positive. So That's an open question. This is a this is a great open question. I don't know the examples. All the examples we know, this set has at most 2 elements, but we don't know if it is finite or not. Recall that we know that this bounded above. But well, about openness. Can the image of Ricci tilde, which are the solvable T's, be open? We'll show that that never happened. But we don't know if it is always open on the positive T's, on the metrics. Okay. In all the examples we have seen in all the papers, you have that this is open in MG. Well, this concept of invertibility, if it is, the question if it is related, okay, to Ricci tilde being a local diffeomorphism at the metric G, and the answer is yes, it's equivalent. That's our first theorem. And well, remember this isometry class. We talked about it. I mean, in any other geometric problem, I mean, if you are studying Einstein metrics, of course, all these orbit are all Einstein metrics and they are equivalent. So you have nothing new. But in this problem, it may give you some information, because if you are asking about the rank of this function, you can study first the rank in this subset, okay? And if you are if the image here already reduced in 1 dimension or 2, then you are getting that it's not invertible, it's not Ricci local invertible, okay? So you may prove that your metric is not Ricci locally invertible by just studying here, which of course is related with this phenomenon that Ricci may have more symmetries than the metric, right? That's exactly what I'm saying. If the rank is not, if it is not surjective, okay. I mean, if the dimension of this is less than the dimension of this orbit, okay. And so we also have the question of signature, which are all the possible signatures of the Ricci tensor. Okay. Well, there is a relationship with invertibility, because if you have that the Ricci tensor has signature P positive, N negative, and Z zeros, and it is Ricci locally invertible, then you are getting all these signatures for free, because the zeros, since locally all these T's are attained, then all these zeros can be made plus or minus as you want. But just that, okay. So let me to warm up with an example. This is maybe the simplest example. You may think it's a baby example, but it's a very illuminating baby. This is Berger spheres. Okay, we are on the 3 sphere. This is G, so we are studying left invariant metrics on the sphere with an extra symmetry. Okay, then these are the G-invariant metrics depend on 2 parameters, A and B, positive. These are this is MG. And we take this line, GB, 1BB, I'm, okay, A is 1, and I'm drawing only 1B. And well, we have here the round metric. This is the Ricci positive region. This is the scalar positive region. This blue metric has scalar curvature 0. And here you have negative scalar curvature. And then, well, which are the possible Ricci tensors, okay, of all these metrics? I choose a line because remember that the Ricci tensor is scaling invariant, so you'll get a curve, okay? And this is the image of Ricci. These are all the all the Ricci tensors. This is the formula, very simple, okay? And well, here you have the round metric, and you can see that in the positive region, for positive tensors, up to scaling, for any T positive, there is a unique C such that there is a solution for CT, okay? So you can solve the problem for any T here with uniqueness, unique C and unique G. But here, as you can see, these red metrics, they, okay, it's like you have, for this T, you have two solutions. Think that the T is here. You have one C1 and a metric GB, and one C2 and this other metric. Okay? And so in this very simple example, you already get non-uniqueness of the constant and of course the metric. Okay? And these two metrics, as you see, recall that as you see, that one of them has positive scalar curvature and the other one negative, but the same Ricci tensor up to scaling. Okay. So already here you already, I don't know, see this phenomenon. And well, this blue metric, which is precisely when this line is tangent to the image of Ricci, cannot be invertible, because as you see, there are T's here for which there is no solution. And you can go closer and closer with these two red metrics, and you're proving that the Ricci tilde function is never injective in any neighborhood of the blue metric. Okay, so everything is failing for invertibility, and is precisely the metric with the scalar curvature 0. So this is the image. These are the T's for which there is solution. The image of Ricci tilde, as you see, is open here, but it's closed here. So it's nothing. It's not open. Okay, and you can see clearly here that this blue metric does not have a neighborhood where you can solve the problem, the PRP. Okay. Okay, so very simple but very, very nice example. Well, the variational principle in the homogeneous case, what we have here is that in this manifold, we have this Riemannian metric. At every metric G, you take this inner product on the tangent space. So this is defining a Riemannian metric on MG. And it is well known that the gradient of the scalar curvature functional, it is precisely Ricci, minus Ricci, minus the Ricci tensor. And so, for any fixed T and a metric G, the following are equivalent. I mean, this, which is the gradient of scalar curvature, is a multiple of T if and only if this, right? I'm saying nothing here. If and only if is orthogonal to the orthogonal of T. But then you get this principle, because the orthogonal of T is precisely the tangent space of this submanifold of metrics having trace, satisfying that the trace of T with respect to the metric is 1. Okay, so you get this way to see the solutions. Okay, we are assuming that the trace of T with respect to G, the original G, is 1. But so the scalar curvature is Z if you take trace here. And so what you're getting, if recall that C is positive for us, so you are getting that the pair G with plus or minus a scalar curvature is a solution to PRP2 for plus or minus T. Okay. That's the variational approach. And know that you may be losing solutions with 0 scalar curvature, but they are the critical points of the scalar curvature function restricted to the trace 0 manifold, submanifold. Okay. This principle has been applied very successfully in the last 5 years, obtaining, well, very nice sufficient and necessary conditions for the T's, the solvable T's on many kinds of homogeneous spaces. In the compact case, mainly for T non-negative, and the critical points were all maxima, if I remember well, in the compact case, and uniqueness always holds. So the papers are by Pulemotov, Gold, Pulemotov. They obtain results for generalized Wallace spaces, flag manifolds, and homogeneous spaces with 2 irreducible isotropic summands. Then Wadsworth, Pulemotov, Rubinstein, Ziller, spheres and projective spaces. They study a beautiful problem called Ricci iteration that I won't talk today. But and then in these other papers, the famous dRic metrics are studied. These are just K-invariant metrics on a compact simply group H. Okay, Datry and Ziller prove that they are all naturally reductive, and actually when G is simple, they are precisely the metrics which are naturally reductive on left invariant metrics on G. And in the non-compact case, you have to take K, the maximal compact subgroup, also get naturally reductive. And Caroline Gordon worked with that. I will come back to these examples, but they obtain a lot of exotic behavior for critical points. And in this non-compact case, here T cannot be positive, right? But here they obtain different kinds of critical points, not only maxima, and non-uniqueness of C occurs. Okay, in dimension 3, you can fix this basis and obtain and study left invariant metrics on 2 groups, on SU2 and SL2R, depending on epsilon -1 or +1. The formula for Ricci is very easy to get. It's in many papers. And well, Hamilton proved that for any positive t, there exists a unique solution to the problem. We have also these curves of metrics going to the same tensor. So this metric cannot be Ricci locally invertible. And Bosworth completely solved recently the problem on all unimodular three-dimensional Lie groups with this approach. Well, then we have this that Ziller metrics. In this case, remember, we have left invariant metrics on H, which are also K-invariant, fixed as a background metric the minus killing, and take a decomposition as usual. Just assume that A is K irreducible, and these Ki are either simple or one-dimensional in the center. Okay? And well, you have a very nice formula due to Datry and Ziller that for any metric G, which depends on parameters A and B1, B2, Br, the Ricci tensor is precisely this. And then you can solve completely the problem for the PRP1 without the C, because you can write this TA in terms of the TIs, and is unique, as you see, is unique. The solution G up to scaling, of course. And well, in this paper, they study the variational aspect of the functional for all these metrics. This is one of the cases that you understand perfectly the PRP1, but a description for PRP2 is, for instance, we cannot prove that if it is always the case that the image of Ricci tilde is open in the positive T's. Okay, so let's come back to this concept of Ricci locally invertible. And so let me state our results. The first one is this equivalence. G is Ricci locally invertible if and only if Ricci tilde is a local diffeomorphism at G. So you can study that with the inverse function theorem. And if and only if this. So if and only if then Ricci has maximal rank. Recall that Rg is always in the curve of the differential of Ricci. This is the derivative. Okay, it's always here. The question is that's it. That there is nothing more in this kernel. Okay, but to get the equivalence, you have to add this, because recall in the Berger spheres, we had this condition was satisfied by all the metrics, but so the problem was in the blue metric with the scalar curvature 0, and it's because of this. And you need both to get the invertibility. And our second main result is that if you take an irreducible metric, which is naturally reductive with respect to G, that means that with respect to some reductive decomposition, I will define naturally reductive in a minute, and the scalar curvature is 0, then is Ricci locally invertible. Okay, so, and we are not assuming G compact. I forgot to say that. Okay, G is any Lie group. Okay, and so what we have to understand then is this first variation of Ricci to study this condition, which is the Lichnerowicz Laplacian. Okay. Yeah, time. We are like in the middle of the talk.
Maybe a bit
Yeah.
further away.
Okay. This part of the talk is not virtual. It will be very technical, more technical. I mean, but well, is the way you have to take a to make computation, right? To compute curvature, to compute anything, you have to take a reductive decomposition and make identifications. So let's do that. Let's do that. The tangent space is now P, and then we can take all the tensors of metrics on P. And if you further fix a background metric, then you can identify with operators. We like operators more. So instead of tensor, you can think in operators. Okay, these are the identifications. Okay, here there are two H's instead of one, like in the tensor, but it's just is convenient. It's the same reason why the Ricci flow equation has a 2. Okay, so the choice of a reductive decomposition, sometimes one just say, well, but it may be crucial, okay? There are too many possibilities, and you may be losing a property like this, for instance, if you don't choose carefully. This is a wonderful property. It's called naturally reductive with respect to G and the reductive decomposition. When all these adjoint maps, but restricted to P and projected on P, are skew symmetric. Okay, geometrically is that this curve is precisely the geodesic with this direction. Starting in our origin point, okay? Well, the moving bracket. So let's call mu to the Lie bracket of G, and mu P is to restrict mu to P times P and then project on P, okay? This mu P is 0 if you have a symmetric space, for instance. And then for each positive H, K invariant, to have a metric, we consider a new Lie algebra, which is this one. This is the usual action of GLG on this space of skew symmetric brackets. But then H bar defines an isomorphism between this Lie algebra, which determines an isometry between these two homogeneous spaces. I mean, G, K plus P is a reductive decomposition for all these homogeneous spaces. And then on the left, we are moving all K invariant metrics. And well, on the right, we are varying the Lie bracket instead of the metric to keep fixed this background metric. It's just a point of view, okay? If we assume G unimodular, then a formula for the Ricci operator is this one, where B mu is the operator of the killing form, and M is the moment map for this representation. So this is the way we see the Ricci curvature. Okay, let's explain this moment map. This moment map is defined like this, where theta is the usual representation on this kind of tensors, brackets. Okay, but then it's like then we study, I don't know, Einstein metrics, Ricci flow, anything, trying to use properties of M, because the killing form is easy. I mean, is easy to control. The problem is this one, okay? So this is really the heart of Ricci, the moment map. For instance, the scalar curvature is just the square norm of the bracket. And then, well, you can use GIT properties of the moment map to study Ricci. Okay. So this is the Ricci operator, and we had to compute the first variation of this operator M to study the behavior of the Ricci flow years ago. And this is the formula, which is this delta mu p is just the representation, the action of GLP on mu p on the Lie algebra. And then you take the transpose and you have, well, a lot of property. The first variation is this operator, and this is related to Chevaley cohomology, which is the cohomology of Lie algebras with values in the adjoint representation when k is trivial, that p is g. Then this is the first part of the cohomology. And then if you take the Laplacian, as usual, that the kernel of this Laplacian is the cohomology, then this operator, the first variation, appears here. Okay. So the PRP problem is therefore equivalent from this approach of moving brackets to study this function. And since we have this isometry from this point of view of varying Lie brackets, then we get that what we have to study is this operator. Instead of the Ricci operator, is H Ricci H. Okay, that's Ricci bar. And this is the operator you have to use to study the PRP. Okay, so now for any operator T, you want to solve on H and C. But everything is written as symmetric operators. And so, well, we have the first variation of Ricci Barra, which is what we need to use the inverse function theorem. And recall, well, we use this result by Wang. On this delta G is kind of a transpose of the Lie derivative, doesn't matter. But in the homogeneous case, the first variation of Ricci is the Lichnerowicz Laplacian, okay? And so what we are getting here from the point of view of the moment map is really a formula for the Lichnerowicz Laplacian for any homogeneous space. Of course, the question is how useful is this formula, but well, so this is the formula. Yes.
Do you really mean AM plus MA in the lemma?
Yes, because A is symmetric. Yes.
No B.
No, B is gone because it's like B is constant.
Okay.
You see here, it's like in the formula for the Ricci tensor. It's always the killing form is fixed, and then when you check the derivative, it's gone because it's a constant part of the Ricci tensor.
Okay.
That's a huge difference with the Ricci operator. But here it doesn't depend on H. Okay, so that's why the killing form is gone. And well, we have this formula, and maybe I will skip this. This is the thing on the direction on the equivariant isometry class that you may get many examples which are not Ricci locally invertible, but let's go to the naturally reductive case. We don't have time. The thing is that if the matrix is naturally reductive with respect to G and some reductive decomposition, then everything simplifies in a very strong way. Okay, the moment map, as you see, the moment map is just this. So if K is trivial, okay, is the Casimir operator for the adjoint representation. If K is not trivial, well, it's like a quasi-Casimir, but yeah, very different because it's very difficult to get some result using representation theory, but at least it's a quasi-Casimir. And also, we introduced this operator CP. Recall that all these maps are skew-symmetric, so this is again symmetric if A is symmetric. And well, the operator is non-negative, and the kernel is precisely the A's commuting with all these maps. And well, again, if K is trivial, you cannot see, well, sorry, but is now the Casimir operator, but for this representation, for the symmetric of G, okay? And why I'm introducing this CP? Because in the natural reductive case, the Lichnerowicz Laplacian or first variation of Ricci is precisely CP. And then you get this theorem. Well, it was time for the first proof of the talk. You have then that if it is irreducible and naturally reductive and non-zero scalar curvature, then it's invertible. And well, the proof is just that if G is irreducible and naturally reductive, then there are no non-trivial subspaces invariant by these two. This is not a Lie algebra, but this is a subspace of operators. This was used by Constant and, wow, 56. Constant and that is Ziller, that you, I mean, if P decompose under this action, P1 plus P2, then it's not hard to see that you get the same as for symmetric spaces, okay? That really you have the product of two naturally reductive spaces, and then since G is irreducible, you cannot have that. But then if there are no trivial subspaces, the kernel, which is here, is just are just the multiples of the identity. So the kernel of the differential of Ricci are just the multiples of G, and that's it. And okay, the consequences, the applications are like, well, for G compact, you always have these normal metrics, right? That they are just restrictions of B invariant metrics on G to P, which are, of course, always naturally reductive. And so they are invertible because the scalar curvature is always positive. Well, you have this very nice Ziller metrics. And well, to get irreducibility, you need to assume H simple, okay? If H is simple and the scalar curvature is different from 0, then you get invertibility. In the non-compact case, the same. And there are also some nilpotent Lie groups. Caroline found these two-step nilpotent Lie groups admitting naturally reductive metrics. And so in this case, if n is indecomposable, also you get invertibility. And then you have the structure theorem by Caroline that like any naturally reductive space is actually like a kind of a, I don't know, I use this, I don't know if this word exists, amalgamated or construction of these three types, okay? But in a very specified, rigorous way, of course. Okay, so in the naturally reductive case, then we have this corollary that the Lichnerowicz Laplacian is precisely this operator CP, okay, and so this may have some application. We are actually working with Emilio, some work in progress on stability of Einstein metrics, not only stability, I mean rigidity, how do you say this, infinitesimal deformability. You can apply this formula to study all these problems for Einstein, naturally reductive metrics, homogeneous of course, by computing or estimating the first eigenvalue of this operator CP. Okay, but okay, in my next talk, I will go slowly on this last part and clarify some things and add some results, kind of green result, but we have some results on the critical points by using the second variation of the scalar curvature, which is very, very similar to the first variation of the Ricci curvature. And my next talk is in 1 month in this conference. I wanted to advertise this conference. Is for the birthday of Dmitry Alevsky, okay, in September. This is not a typo. It's 80. It's not 60. Incredible, running and swimming every day still. And okay, thank you very much.
Thank you, Jorge. Are there questions?
Yes.
Uh-huh.
All right. A whole bunch, so please tell me when to stop. So let's see. First, I'm wondering what your result about local invertibility means for the openness of the set of tensors. So do I understand correctly that if you had invertibility for not just naturally reductive metrics, but for all metrics, then you would be able to conclude that the set of Ricci curvatures is open, and this is a step to that. Am I correct?
Yes, but yeah, that never happens, but yes. It never happens because you always have a metric with a scalar curvature 0.
Yeah, okay. Right.
That's why, because, okay, you cannot have scalar curvature bounded below, okay? So that's why only in very, very exceptional cases that Ricci is constant, product of isotropy reducible spaces, that the Ricci is constant function, then
Sure.
It's not invertible either. Yeah, but yeah, you never get this that the Ricci tilde is a local diffeomorphism in the whole MG because of the scalar curvature.
Because it's, that makes sense. And if I could ask one more, first of all, that you get, as far as I remember, all the results that I've seen before, delay, the stuff with Herzlich, all that, they could only prove local invertibility around an Einstein metric, right? For an Einstein metric. So I think the fact that you can do it for naturally reductive is very cool, is very impressive. I mean, I understand that we're going into the homogeneous setting and it's a little different, but still I think it's very cool. The question though is, do you think that your formula could have proved the convergence of the iteration near a homogeneous Einstein metric? For example, if you start with a homogeneous one.
We were working on that few days, but yeah, this is work in progress. We are still, but yeah, I think it may be useful to get, yeah, to understand, to get more examples of metrics which are attracting the Ricci iteration. Yeah.
Right. Actually, in this theorem that's on the screen right now with Amelia Lauret, you say stability. Do you mean under the Ricci flow?
And many kinds of stability. The classical one for as critical point of the scalar curvature, but you also have this new stability by the Perelman functional.
Okay.
The Perelman functional, yeah.
Okay.
And so all these operators, Lichnerowicz, Laplacian, they are all, yeah,
I see.
related, and you always, yeah, the first eigenvalue is the
All right. Well,
the target, yeah.
yeah. Excellent. Thank you. Well, very interesting talk. Thank you.
Thank you.
Karen, I think you're muted.
I'm sorry. I was asking if there were any other questions first. And if not, thank you very much for a very nice talk. And our next talk in 2 weeks will be by Anna Siffert at the University of Münster. And again, the time rotates, so the next one will be, I think, noon UTC time, which of course varies depending on your location. So thank you.